Let's look at what factors affect the power of a z-test. I'm going to talk about this in the context of a test on one population mean, but the same general ideas would hold for many other types of tests as well. Suppose we are about to randomly sample 20 values from a normally distributed population, where the population standard deviation sigma is known to be 10, but the population mean mu is unknown. And we wish to test the null hypothesis that the population mean is 50 against this one-sided alternative hypothesis. In this case, the appropriate test statistic is this z-test statistic. The power of this test is the probability of rejecting the null hypothesis when it is in fact false. Loosely speaking, it is the ability of the test to detect a false null hypothesis. Power depends on a lot of factors. It's going to depend on the significance level alpha, the hypotheses, the population standard deviation sigma, the sample size n, and the true value of the population mean mu. Let's look at an overall summary before we look at each one of these individually in greater detail. Holding all other factors constant, power will increase as the significance level alpha increases, as the sample size n increases, as the population standard deviation sigma decreases, and as the true value of mu gets further from the hypothesized value mu naught, as long as it is in the direction of the alternative hypothesis. For two-sided alternative hypotheses, we wouldn't need the part in brackets. Recall that we're testing the null hypothesis that mu is equal to 50 against the alternative hypothesis that mu is less than 50, and suppose we feel that a significance level of 0.05 is reasonable here. Since our alternative hypothesis is that mu is less than 50, we put our entire alpha level into this left tail of the distribution. And so we are going to be rejecting the null hypothesis if the value of the z statistic that we get is less than or equal to minus 1.645. I'm now going to re-express that rejection region in terms of the sample mean x bar, because that will help us visualize a few things later on. Our z-test statistic is x bar minus mu naught over sigma over the square root of n. And we're going to be rejecting the null hypothesis if that is less than or equal to minus 1.645. Using a little algebra to isolate x bar, we'd see that we reject the null hypothesis if x bar is less than or equal to mu naught plus sigma over the square root of n times minus 1.645. And putting in the values for our situation, that's x bar less than or equal to our hypothesized mean of 50 plus sigma, which was 10, over the square root of 20, our sample size, times minus 1.645. And multiplying all of this out will reject the null hypothesis if x bar takes on a value that is less than or equal to 46.32. So what we've done here is re-express the rejection region, which was once in terms of the test statistic z, in terms of the sample mean x bar. Here's what this looks like visually. The white curve represents the sampling distribution of x bar when the null hypothesis is true. And we are rejecting over here in this left tail, putting our entire alpha value of 0.05 in this left tail. And we're rejecting the null hypothesis if the sample mean takes on a value less than or equal to 46.32. Now let's look at what factors affect the power of the test. All else being equal, the further mu is from mu naught in the direction of the alternative hypothesis, the greater the power of the test. The bigger the difference between the true value of the population mean mu and the hypothesized value, the easier it's going to be to detect that difference. Let's see what that looks like. The white curve here represents the sampling distribution of the sample mean when the null hypothesis is true and mu is actually 50. The blue curve represents the sampling distribution of the sample mean if the true mean is actually 49. And recall that we are rejecting the null hypothesis when we get a sample mean that's less than or equal to 46.32. And so the green shaded area under the blue curve is the power of the test when mu is actually 49. But what happens as the value of mu gets farther and farther from the hypothesized value of 50? As this blue curve moves farther and farther to the left, well, the green shaded area is going to get bigger and bigger. So let's let mu decrease and watch what happens to the power. When the true value of the population mean mu gets far enough away from the hypothesized value, then the power of the test is going to be nearly 1. Here's another way of visualizing what we just looked at. Here's the power curve for various values of mu. And near the hypothesized value of 50, the power is going to be very low. But if the true value of mu is actually far away from the hypothesized value, down here near 40 in this case, the power is going to be nearly 1. But that power also depends on the significance level, the population standard deviation, and the sample size. So let's take a look at those as well. All else being equal, the greater the significance level alpha, the greater the power of the test. Here again I've plotted out the sampling distribution of the sample mean when the null hypothesis is true, and the gray shaded area is our significance level alpha, 0.05 in this case. But if we were to let alpha increase to 0.1, then this shaded area of alpha is 0.10, and we've made it easier to reject the null hypothesis here. And since it is easier to reject the null hypothesis, our test will have greater power. Here's a summary of the power curves for various values of alpha. Here's sigma as 10 and n as 20, but we're going to let those vary a little later on. The red curve represents the power function when alpha is equal to 0.01. And since we've chosen a small value for alpha, we're making it difficult to reject the null hypothesis, and the test is going to have lower power than if we chose an alpha value that was a little larger. But here still, when the true value of mu is far enough away from the hypothesized value, the test has power very near 1. All else being equal, the greater the sample size, the greater the power. The greater the sample size, the more information we have, and the easier it's going to be to detect a difference from the hypothesized value. Let's see what that looks like visually. The white curve is the sampling distribution of x bar when the null hypothesis is true, and the blue curve is the sampling distribution of x bar when mu is actually 48. I've changed the scaling from previous plots here so that I can keep the scales the same for the different plots I'm about to show you. The standard deviation of the sampling distribution of x bar, sigma x bar, is sigma over the square root of n. So as we let this sample size increase, the standard deviation of these distributions is going to decrease, and this green shaded area representing the power of the test is going to increase. And if we made our sample size large enough here, the power would become nearly 1. Here are some power curves for different sample sizes when sigma is 10 and alpha is 0.05. The red curve here represents a sample size of 10, and we can see that the power is less than when the sample size is larger. All else being equal, the smaller the standard deviation sigma, the greater the power of the test. The smaller the standard deviation sigma, the less uncertainty there is, and the easier it's going to be to detect a difference from the hypothesized value. Here again, the white curve represents the sampling distribution of x bar when the null hypothesis is true, and the blue curve is the sampling distribution of x bar when mu is actually 48. The green shaded area is the power of the test when n is 20 and sigma is 10. Recall again that the standard deviation of the sampling distribution of x bar is sigma over the square root of n. So if sigma were to decrease here, the variability in these curves is going to decrease, and the green shaded area representing the power is going to increase, in much the same way as when we looked at the sample size increasing. So let's let sigma decrease and watch what happens. And if sigma were to get smaller and smaller, the power would get very close to 1. Here are the power curves for various values of sigma when n is 20 and alpha is 0.05. And the red curve here is a standard deviation of 20. So when there's more variability than in the other two cases. And when there is greater variability, there is greater uncertainty, and we have a lower power of the test.